Okay, so for this question, we're going to find our target in a sorted matrix. And this matrix is sorted in each row and each column, but we're not sure that every first element of an row is always larger than the last element of the last row. So as we can see, we're giving a matrix, which is a 2D array and an integer target, and we're going to return a Boolean variable. So let me check. So are the elements in this matrix unique? Yeah, but I think it doesn't matter that much if it's not unique, right? So can I just assume that if there are multiple results, then I will just return any of them? Oh, no, I'll just return true. Yes? All right. So I think we can apply the binary search idea to this problem. So like in the ordinary 1D array, the left end of the array is the small direction, and the right end of the array is always the big direction. And then every time we find the middle element of the search space and compare it to the target. So, but then here we don't have left or right, but we know that the upper left corner is always has the smallest values, while the right bottom corner always has the big values. So we so that is kind of similar to the 1D array, and just like the binary search on 1D array, we can start by examining the middle element value and compare it to the target. And then here in our 2D sorted matrix, the middle element should be the right upper corner and the left bottom corner. So I think first we will start. So let me take an example. So for example, if our matrix is like this, and 2 and 4 and 7, 3, 5, 8. All right. Then, for example, we can start from the middle. So for example, here the left bottom corner. And let's say our target is, let's say, 6. Okay, then we start from here and we compare the middle element value to our target, which is 6. And as we can see, the middle element value is smaller than the target. Then we should move to the, then it means that we are smaller and we should move to the, toward the big direction. And in here, in the 2D version, the big direction should be the right bottom corner. So here we can move right. Yeah, so like for this for the 3 here, for this element, it has 2 options to move for the next move. Either move upward or move right. And the upward direction is the smaller direction, and the right direction is the bigger direction. And because 3 is smaller than 6, then we should move to the big direction, which is we're going to move right, move toward the right bottom corner. And so here we know that 3 is already the largest element in this column. So everything that's above 3 in this column are smaller than the target. So we can just discard the whole column that 3 is in. So now we know that the first column does not have our target. And meanwhile, we are going to move right. So we can increment the column number by 1. So here the column number should be, so initially column number is 0, and now the column number is 1. And then we're here 5. So again, we compare 5 to the target value, and it's smaller. So again, we move right. And meanwhile, we discard the whole column that 5 is in, and now column should be 2, and we're here. So it's 8. And because 8 is bigger than our target 6, so we're going to move to the small direction, which is we're going to move upward. So the row number, should be, so initially it is 2, and now it should be 2 minus 1, which is 1, and we're here, and it's still bigger than 6. So we will decrease the row number by 1 again, and it will become 0, and then we're here. And we find our target, and we can just return true. So in this way, we can apply the ordinary binary search idea on the 2D matrix. So in this way, if we start from the left bottom corner, then our row number is always decreasing for at most m times, while m is the number of rows of the matrix, while the column number is always increasing for at most n times, while n is the number of columns in this matrix. So in total, this pointer can move at most m plus n times. So this should be our runtime, which is and it is linear to n plus m. So this may be a solution. And I think another solution is that, so let's say if the m and n, the difference of m and n is really huge. So let's say like we have 2 or even just 1 row, but we have 9 or 10 columns. So anyway, so it's really so like m is really bigger, is a lot bigger than n. Then if we're still using the previous solution, then we're going to examine the element one by one, right? But obviously we can just apply a binary search on this and make our runtime logarithmic. So I think the idea is that for m and n, if the difference between them are really huge, Then for the big one in M and M, let's say M is the bigger one, right? So for the big one, we can apply binary search. And for the smaller one, we can examine it one by one. So let's say we have we have two rows here in this matrix, and it's really wide, but it only has two rows. Then for the rows, like for these two rows, we're gonna examine these two rows one row by another. But for each row, inside each row, for all the elements with different columns, we're going to examine them with binary search. So I think in this case, we're going to run binary search 2 times, and that makes our total runtime n times log m. Right, so this should be the solution. And so yeah, so this should be it. And actually there should be another solution, which is so let's say if our search space is a rectangle, right? Like a big matrix, then we can run a binary search alongside the diagonal, and we can find a split point where we can split this matrix into 4 submatrices with this split point. And then the upper left submatrix, all the elements in the upper left matrix are all smaller than our target, while all the elements in the right bottom corner are all bigger than our target. And then so we can discard those two submatrices, and we're just only not sure of the other two submatrices. So then we can recursively run search on these other two submatrices, so that in the end, after we have examined all our submatrices, we can know if the target exists in the matrix or not. So this can be another solution. And in this way, there's a recursion. We're using recursion, and if we're using the master theorem to calculate its runtime, then the runtime should be Tn should be equal to, so there should be two sub problem for each problem, like two sub recursive calls for each function. And then the size of the problem should be only a quarter of the original size. And the cost of work done outside of the recursion will be log n, because we're using binary search alongside the diagonal to locate the split point. Yeah, so for this, we know that A, which is the number of subproblem, should be 2, and B should be 4, and C, which is the exponent of n, should be 0 here, and P, which is the exponent of log n, should be 1 here. And so because let's check log base A of B and C. So log base A of B should be 1/2. So it should be bigger than C, which is 0. So um, the first case applies, which means that the big O should be n should be squared n. Yeah, and this is the time complexity, and for the space complexity, because for each call we're going to have two sub calls, and then so the time the space complexity is proportional to the height of the recursion tree, which should be log n. Yep. And here n is the area. So if we're using the n and m, which is the dimension of the matrix again, then we know that in the end, time complexity should be big O of squared n times m, while space should be log n times m. So here there are three solutions in total. And which one is better? We can compare it in two different situations. The first situation is when this matrix is a rectangle. Yeah, so this rectangle is when the dimension of the matrix is almost the same or exactly the same. So it's very close to a square. This is the first situation. And the second is that the difference of the two dimensions of the matrix is huge. So it's very far from a square. So let's say, so the first solution is n minus n and constant space, and the second is n log m when m is the bigger dimension and also constant space, and the third solution is square root of n times m, while log n times n space. So these are the three solutions. So for the first situation, when n is equal to m, then here it will be 2, and for the second solution it will be n log n. For the third solution, it will be m, just m. And then for the second solution, when m is a lot bigger than m, then here in this case, the time complexity will be m, and for the second solution, the time complexity will be log m, and for the third solution, the time complexity will be square root m. Okay, so let's see. If it's the first solution, then obviously the first and third solution has the same time complexity, but the third solution requires more space. So the first solution is definitely the winner. Well, if it's the second solution, then the first solution really does not have a good time complexity. Well, the second solution has the smallest time complexity. And also, it's only using constant space. So the second solution will win. All right. So it seems that the third solution does not win in either of the situation. So I guess I'll choose the first and second solution. And then so for here, we're going to use all those three solutions. Now, we're going to check the first solution first. Solution 1. All right. So we're gonna do some sanity check. If the matrix that given is not valid, or its length equals to 0, or actually we can check the smallest and biggest element of this matrix. Okay, let's initiate some variable. So let's call the row length is the number of rows of the matrix, while the column length is the number of columns of the matrix. Okay. So the most upper left element should be the smallest element. And if the smallest element is still bigger than the target, then we know the target must not exist in this array, in this matrix. Or likewise, if the most right bottom element, which is the largest element of the matrix, is still smaller than the target, then we know it's impossible that the target will exist in this matrix. So in all those cases, we will just return -1. Oh, sorry, we'll return false. Yep. Then we're going to check the middle value. And here, here, so we're going to have a pointer. So we're going to initiate the row number of the pointer to row length -1, which is in the last row, and the column number of the pointer to 0. Then the column number is going to keep increasing while the row number of the pointer is going to keep decreasing. So, and they're going to stop until row until they are outside of they will be outside of the matrix. So when the row number is still larger than or equal to 0 and the column number is smaller than or equal to the column length -1, which means this pointer is still inside the range of this matrix. Then, okay, we're going to get a current value, like the middle element value, which should be just the row and column of the pointer. Then we're going to compare it to the target. So if they're the same, then of course we find our answer and we can just return true at this moment. Or else if the current value is smaller than the target, then we should keep looking in the large direction, so we're going to move right, which means we're going to increase the column number. So likewise, if the current value is larger than the target, so we're going to keep looking in the small direction, so we're going to decrease the row number. And we were outside of the loop and we still haven't found anything, then we can return false because we know it's not inside of the matrix. Okay, let's run some example on this code. So let's take this example. All right, so at first the row length is 3 and column length is also 3. And then 1 is smaller than 6. 8 is bigger than 6, so we know we can search in this matrix. All right, and then at first row is 0 and column is, oh, sorry. Row is 3 and column is 0. And the loop invariant still keeps. And the current, so at this point, the current value is 3. And it's smaller than the target. So the column number will be 1. Again, we enter the loop and the current value will be 5. And the current value is still smaller than the target. So again, increase the column number by 1, so it will become 2. So at this point, our current value will be 8. And it's bigger than the target, so we will decrease the row number by 1, and then row number will be 2. And the current value should be 2, 2, 2. Wait, oh, I was wrong before. So initially the row should be 2, and now it should be 1. So now the current value is 7 here, and it's still larger than the target. So we're going to decrease the row number by 1 again, and the row number will be 0, and then we're here. And again, we enter the loop, and the current value is 6. So we just return true. Okay, so this is the normal case. So let's say if we only have one value, like one element in this matrix, then here the row length would be 1, and column length should also be 1. And then we compare it to the target value here. Is it bigger than the target? No. But it is smaller than the target, so just return false. Okay. So I think this solution should be right. All right. So this is the first solution. And then we're going to write another solution. And I'm gonna call it search matrix 2. Get a matrix and a target. Then, okay. So again, we're going to get the row length. So up to here, it should be the same. And then, so we're going to check which this 2 dimension of the matrix which is larger. So we can have a Boolean variable called row bigger. So it will be true if the row length is larger than column length. It will be true if it is if the row length is larger than the column length, or it will be false if not. And then, so for here, if let's say if the row is actually bigger, then we will have a matrix like this. So for example, like 1, 2, 2, 5, 3, 6. Well, just something like this. Then if the row is actually bigger, if the row number is actually bigger than the column number, then for each row, so the row number, um, and then the number of iteration depends on the row bigger. So if row is bigger, then we're going to examine the row one by one. And so then the count should be should be the number of rows. So it should be row length, or we're going to examine column by column. Then it should be the column length. Yep. And so for int I is 0 and I is smaller than count. So I'm gonna write another method called binary search here. And we're going to give it the matrix and the target and the I, so we know which row it is searching at this point. And if we find our target in any row, then we can just return true. Or if we have searched all the rows but haven't find anything, then we can return false. Okay. Then here, I'm gonna have a binary search, and we're giving and matrix and an int target and int I. Then we just run the ordinary binary search. So we have a left pointer and a right pointer, but the right pointer, oh wait, we should also pass the row bigger variable. If the row is actually bigger, then we're running the binary search on each row, and that makes our right pointer to the column number. So it should be or if it's not, then likewise it will be the row number. Yep. And then while the middle will be and the current value will be matrix. Okay, again, it depends on if the row is bigger. If it is, then it will be matrix. Its row number will be I, and the column number will be a mid, and otherwise, the row number will be mid, and the column number will be I. Yeah. And so if the target value equal to the current value, then we can already return true. Else, if the target is smaller than the current value, then we're going to search in the small direction, and we'll just make the right else we will keep searching in the big direction and move and make the left increase left to mid +1. And after this, if we haven't find anything, then we can return. Then it means the target does not exist in this row or in this column, and we can return false. Right. So this should be the second solution. And then for the third solution, okay. Search matrix 3, and given a matrix and a target value Then the sanity check are the same. All right, then we're going to search matrix. Then we're going to have a recursive function. Return called search sub matrix. And then we're giving the matrix and a target and the ordinate, the coordinate of the leftmost element and the right bottom, the left upper corner element and the right bottom corner element. So it should be 0, 0, and matrix and matrix. Okay. Well, I'm going to call the left upper corner element as small, and the right bottom corner element as big. All right. And first is the base case. So for the base case is so the small pointer coordinate will keep increasing while the big pointer coordinate will keep decreasing. So the base case should be when they meet each other and they pass each other. So it should be the small row is already larger than the big row, or the small column is already larger than the big column. This is check if the coordinate is valid, and now we're going to check its value. So if the small element is already larger than the target, then we're sure that this target is impossible to be in this submatrix. Or likewise, if the biggest element is already smaller than the target, then we're also sure that it's impossible that this target can exist in this submatrix. Matrix. just return false. Yep. And then we're going to write the recursive rule. All right, so first we're going to binary search the diagonal to find the split point. Okay. So I'm going to use in like the low and high as the pointers to find the split point. Okay, so the low coordinate will start from the small coordinate, and high coordinate will start from the big coordinate. And then they're going to search. Well, then we're going to get the coordinate of the middle point, which should be and the middle column should be and also the current value, the middle element value should be then we're going to compare it to the target. If the current value is equal to the target, then we can just return true. If it's not, then we're going to search the target in the small direction, which is else we're going to otherwise we're going to search in the big direction. Yep. And so when we are out of the loop, then we have already found a split point. So at this point, we're going to recursively search in the other So at this point, when the low pointer and high pointer are out of this loop, then it should be something like this. So yeah. So let's say here is so here should be the small one, and then somewhere here it should be the high pointer, and somewhere here there should be the low pointer, and then the big pointer should be here. So we're sure that the upper left corner submatrix is discarded, and the right bottom corner is submatrix is already discarded as well. And so we're going to search in this two. They are the two submatrices. So it should be search submatrix. So as long as there's one submatrix that has the target, then we can return true. So here it should be sub matrix and target, and then well, so here the row should be the small row, and the column should be low column, and its right bottom corner, the row should be the high row, while the column should be big column. Okay. And then for this matrix, then the upper left column should be low, the row should be low row, column should be small column, and its right button corner, its row should be the big row, and its column should be high column. Yep. So this should be it.